Kabanets, so the bar on seconds and book.
Thank you, Rahul. Welcome. So please ask any questions you like during this tutorial. It's supposed to be pretty basic stuff. So apologies to the experts in the area, you'll be bored. But I'll be talking about connections between pseudorandomness and learning. And pseudorandomness is really about structure hidden within randomness, so that even though there's some structure, you cannot really tell. Sorry? Oh, I thought it was a question. So yeah, please do ask questions. So pseudorandomness is like you're hiding structure within randomness so that nobody can tell if there's something structured is hidden within randomness. And learning is kind of like the opposite. You're given something which has structure hidden in it or some present in it, and like maybe surrounded by randomness, and you're trying to learn that structure, kind of distinguish it from random, extract it from randomness in some way. So pseudorandomness and learning seem to have this kind of conflict between them. So one is possible only if the other one is not. And that will be the subject of my first hour of talk, where we'll be using MCSP algorithms or heuristics for MCSP to break pseudorandomness, to show that this is not possible, which would imply that this is possible so that we can have learning. Okay, so that will be this beginning. So before I get more formal, let me show you some random picture of a jungle. It's supposed to be jungle, I think, in northern India somewhere. So that gives you enough information to figure out what is in there. Can you see? Oh, very good. Okay. So it's the same picture. I'm looking at Eric. Do you see a tiger in there?
I still see it. Is it supposed to be a color blindness test?
No, no. Well, it depends who you are. If you're some Bardier, then you'll see this picture, and because you cannot distinguish red from green. If you langur monkey, then you'll see, or a human, as it turns out, you will see this picture, so you'll be able to easily tell a red colored tiger from the green foliage. Okay. So depending on the power of your test or your observer, something may look pretty indistinguishable from random, or something definitely is distinguishable from random by a big life-saving margin. So this is pseudorandomness kind of in a nutshell, but there's more going on here. So as I mentioned, like this monkey, and by the way, they often cooperate with the deer, so they act like as a sentry for the deer to make sure that the deer who suffer from this filtering will not be eaten by a tiger. So these guys can distinguish randomness from something that contains a tiger in it. And intuitively, there's a good chance that monkey can see the tiger itself. So monkey can also learn the tiger. So like if you can distinguish randomness from a structure, then you're in a good position to learn what is hidden within that randomness. And that's exactly what I'm going to be talking about next. Any questions so far? So let me define the learning model. So we'll talk about learning model due to Valentine stack, probabilistically approximate learning, where you have uniform distribution, and I'm going to allow membership. I'm going to allow membership queries as opposed to just random labeled examples, as would be the standard for Valiant's model. So the picture looks like this. You have a learning algorithm that tries to learn something like a tiger in some complexity class C, so Boolean function from some class of concept C. And the learning algorithm has access to like a black box access, can ask oracle questions to this function, ask for input X, get back the value of the function on that input X, so like can query the oracle F for a bunch of times, and then maybe use some randomness, and with some decently high probability, close to 1, output a circuit, which may not compute the function f exactly, but is like epsilon close, where epsilon close means that it agrees with the function on all inputs except maybe like epsilon fraction. So that's the model.
Then what is the probability of two probabilities?
Right. So this probability is over the randomness of the learning algorithm. And so the high probability over its internal randomness, the learning algorithm will produce a good circuit. And the circuit is considered to be good if it agrees with the function on most inputs. So this is the uniform distribution that I mentioned here. So the success of the learning algorithm's output, the hypothesis that is produced by the learning algorithm, is judged by how close it approximates the function in question, where the closeness is with respect to the specific uniform distribution. In PAC model, it can be arbitrary distribution that you have no clue about, but this is just for specific uniform distribution. Yeah, thank you for the question.
But the function is worst case.
Function is worst case, yeah. So, well, in the sense that function can be anything. Yeah. It's not like a distribution over functions. That's very good. I'll get back to that in a moment. Thank you. So that was the definition for the learning part. So for pseudorandomness part, maybe superfluous, but let me still define what pseudorandomness means. And pseudorandomness that I'll be talking about will come in two flavors, even though I'll focus on the second flavor, but I will define both. So there's a crypto pseudorandomness and complexity pseudorandomness. By pseudorandomness here, I mean pseudorandom generators. So for crypto, pseudorandom generators are equivalent to one-way functions by this famous result due to Hostad, Impaglazzo, Levin, and Luby. And for complexity pseudorandom generators, their existence is equivalent to circuit lower bounds by this beautiful connection between hardness and randomness due to Nissan-Wigderson and some follow-up work. So the generator is this object, which is an algorithm which takes some string and outputs a longer string, usually a longer string. And the definition of it being good, being pseudo-random, is that the output of the generator kind of looks like it is a uniformly random string to a computationally bounded observer. Like if you're a monkey, then it's very difficult for you, or if you're deer, even more difficult for you to tell something output by the generator from the random thing. And these two settings I mentioned, crypto and complexity. So in the crypto world, your adversary can be an arbitrary size circuit, polynomial size circuit, but of arbitrary polynomial size. And you also require, the generator, is also required to work in polynomial time in the seed size. So you should be very efficient and fool lots of adversaries. So your life is really difficult. Whereas in the complexity world, you're told in advance that you'll be fooling size n square circuits, for example. So you don't need to fool n cubed, just n square. And moreover, you're allowed to run in time, which is like exponential in the seed size. So life is relatively easy. However, so because like the restriction here or the demands here are much more stringent, showing that or killing the crypto generator is relatively easy, whereas killing the complexity generator is more difficult, right? Because it's so close to the real thing, maybe. And so intuitively, if you have something which kills complexity generator, then you should get better bang for your buck. And that's exactly what happens, and that will be the question that was raised earlier. So if you manage to kill cryptographic pseudorandom generators, then you do get a learning, but the learning will not be worst case, but on average. And that's exactly the point. And this is from an old paper by Impaglazzo and Levin, and there's some follow-up work by Blom, first Kearns and Lipton, and now in Yogev, who show this connection. So basically, if you break crypto PRGs, then you get something for learning, but that something is unfortunately only on average. Whereas if you break the complexity PRG, which, as I said, is more difficult to do, then you get learning in the worst case. Okay, and this is what I'm going to talk about. This is based on the work of Impaglazzo and Wigderson, a different paper from '98, from 2001 journal version, and also the work with Carmasino, Impaglazzo, and Kolokolova that I'll focus on most. All right, so what are the complexity generators? And I'm not gonna give like full details, of course, in this tutorial, but I wanted to give some flavor of the very famous complexity pseudorandom generator due to Nissan and Wigderson. I won't define it very formally, but I'll give you the properties of this generator. So this is a generator which is based on some function f. Think of it as maybe a hard function so that the pseudorandomness of the generator will depend on the hardness of the function. So it will be the harder the function, the more secure the generator intuitively. And this generator based on this function will have some stretch, some non-trivial stretch that you can control. You, the designer, can control how much you want to stretch. And say my generator will map n square bit strings to some capital L bit strings, where L can be as big as exponential, but not too big, so like at most 2 to the n. And the nice thing about this generator, which is shared by some other constructions that I'll mention later, is that breaking this generator gives you something nice. In this context, it will give you a learning algorithm for the function f that the generator was based on. And the way it comes about is through this picture here. So suppose your generator is broken by a distinguisher D. What it means that there's this distinguisher D who tells with noticeable advantage the case of the output coming from the pseudorandom generator versus the uniformly random distribution. Then your learning algorithm with help from this distinguisher, so it's learned with Oracle access to D, will be able to learn F. And it will ask some membership queries, as we discussed in the model of learning that we're using here. And after some polynomial amount of time, using some randomness, we'll spit out a circuit, which will be a good circuit for the function f. How good under the uniform distribution? It will approximate the function f better than 1/2. So it's going to be half plus some parameter where this parameter depends on the output of the generator. And it's not what we quite want. It's like a weak learning model, but it can be boosted to strong learning, and I'll talk about that later. So the important thing is that the runtime of the learning algorithm is like polynomial in the output size of the generator. So if you want the generator to run fast, and you want to learn some function f on n inputs, this n square, by the way, will be exactly same n as your function f input size. So if you want to learn function f on input size n, and you use this generator, you want to learn it fast and polynomial in time in n, then you want to make this capital L to be polynomially small. It's kind of the opposite of what you do in like randomization, where this generators come from, where you want to stretch by a lot because you're so greedy, you want to have as many pseudorandom bits as you possibly can. You don't want few pseudorandom bits. But for the purposes of learning, not being greedy is better because it gives you more efficiency.
Can you go back? So you assume that f is taken for some flatted functions, or what?
Yes.
Exactly?
So here it's a template construction of this procedure which maps short strings to long strings, where this template contains a place for function f of your choosing, and you can plug in for f anything you like. And the property you'll get if you manage to distinguish this generator, if you manage to break this generator, then you'll learn this function f that you plugged in. And then because it's worst case function, you can pick it any way you like. You'll be able to learn every function you like. So that will be worst case learn. That's what I mentioned. Yeah, as I said, it's a weak learning, and we'll have we can get strong learning from it by doing some kind of boosting argument that I'll talk about later. Okay, so both of these problems, like pseudorandomness and learning, are of course examples of meta-complexity problems. But there's also like a Kolmogorov relative that is going to be crucial for the story, which is MCSP. Because MCSP is like an ultimate generator killer. So it can kill pretty much any generator, complexity one or cryptographic one, you name it. Because intuitively, the generators are defined in such a way that the output of the generator is compressible to the seed, right? It's the definition of generator that you take a seed and you expand it computationally. So the output of the generator is compressible, thinking about the opposite direction. And MCSP or relatives or Kolmogorov complexity relatives are exactly those algorithms that will tell you if your given string is compressible or not. So the output of the generator is compressible, therefore MCSP will say, hey, it's compressible. And most random strings, by counting, have huge Kolmogorov complexity. They're essentially incompressible. So like on random stuff, MCSP algorithm will say most likely not compressible. On pseudorandom stuff, it will say compressible for sure. So it will break your pseudorandom generator like that. The definition of min-sized circuit problem, I don't have to define it, but I will, is given a truth table of a function f, so the full truth table of size 2 to the little n for your function on n bits, and a size parameter s somewhere between 0 and 2 to the n. The question is f computable by Boolean circuit of size at most s? It was defined as already, but just in case. And the property of this Nissan-Wigderson generator is so-called locality. And this is the term that Rasborov introduced when he used pseudorandom generators, in particular Nissan-Wigderson ones, for the study of proof complexity. So there's another connection between pseudorandomness and proof complexity. And he used Nissan-Wigderson generators and he observed this locality property. What is the locality property? Basically, there's like a technical definition, slightly technical definition that I'm going to say, but basically locality means that MCSP will break your generator. Okay, so if your generator local, if and only if it's breakable by MCSP of some sort. More precisely, locality means that on any seed to the generator, so say you have function f that the generator is based on coming from some size s circuit class. So f is computable by polynomial size circuit. Okay. Then if you use any seed to the generator, the output of the generator using your function and that seed s, when viewed as a truth table of a Boolean function, so you have here short string, the seed to the generator, and slightly longer output, which you think of as a truth table of a function on like log of the length of the string inputs. Right, so if the output of the generator is of size capital L, I will always think of capital L is equal to 2 to the little l. So my function here is the truth table of a function of little l inputs. And the locality means that that function on little l inputs has small size. How big is going to be circuit size of this function? It's going to be the size of s, which is the function f that you use to build this generator, plus some polynomial overhead, which comes from the inner workings of the Nissan-Wigderson generator. Okay, so what does it give you the ability to break the outputs of the generator?
Can I ask a question?
Question,
I'm a
please.
little confused about locality versus non-locality. You explain how MCSP breaks any PRG, and then you said it's local if MCSP breaks it.
Yeah, so basically MCSP breaks a generator because the output of the generator is compressible.
Yeah, this I understand.
Right? But now, what kind of so what does MCSP want? It's not just it's compressible, but it has small circuit complexity. Right? For example, it may be compressible, but in a way, but the circuit complexity may not necessarily be small. Right? There may be a different way to compress it rather than use small circuit to describe it. So depending on who's looking at the output of generators, some things may be breakable or not breakable, depending on the power of the observer, even though the observer may be like MCSP or a relative of MCSP. I'll talk about some other Kolmogorov complexity measure in the second half of my talk. So technically, the locality of the generator means that the output of the generator, viewed as a truth table, is locally computable easily. Locally computable means that there's a small circuit which computes any location of the output of the generator. That's why you think of it as a truth table. You have like a small circuit which computes this truth table. Locality means that this is a small circuit, so you can compute locally in any position. And the size of the small circuit will basically be a function of the size of the function f you start from, plus some polynomial overhead. So if you choose the parameters properly, this size will be relatively small for truth tables of a given length. And then your MCSP with appropriately chosen threshold parameter will say, ah, this is easy because it has small circuit size. Yeah. Yeah, so basically, the output of the generator is like length to the little L. And the size of the circuit that computes this output is this S plus poly N. So there's a bit of translation that you need to do to express this S plus poly N in terms of your input size, which is little L. And like, I won't do the calculations, but I'll show you some two interesting cases. If you have exponential stretch, so your capital L is like 2 to the little n, roughly, and you start with a function f, which is computable by polynomial size circuit, then the output of the generator will be size polynomial in L, because we're polynomial in S plus polynomial in N, so L is polynomial in N, so everything is polynomial. So the point is that you have exponential stretch. The output of the generator has polynomial circuit complexity. Another example, and this will be the setting that we'll actually use. But this is the more standard setting where you have a huge stretch. Backwards. You have huge stretch, there's a small stretch. So if you have stretch polynomially small, and this is the setting we actually want, we have polynomial stretch, therefore our learning algorithm will be fast, we'll run in polynomial time, but you have to pay for it. If you have polynomial stretch, then your input size will be like log n for your function, and the size of your function will be based on this formula over here. If you plug in those parameters, the output of the generator viewed as a truth table function on L bits will be of exponential size in L. So the output is still small, but it now has exponential circuit complexity. So to break this thing with MCSP, MCSP has to work harder, because now you have small difference between like exponentially, but less than maximum, and random, which is basically maximum. So a very small gap in the second case. So MCSP really has to work very hard to distinguish the small gap, versus the first case where MCSP has it relatively easy. You have like exponentially, for random things with exponential high complexity, and for your things it's like polynomials. I have a huge gap between polynomial and exponential in the first case. Easy, hard. In this case, you have a learning algorithm which is sub-exponential because you didn't work hard enough. In this case, because you work so hard, you get as a prize polynomial time learning algorithm. So just again, a pictorial explanation of why is Nissan regression PRG local. Basically, given the seed, the generator, based on the function f, computes the values of the function f from some strings which come from the seed. They have some non-trivial overlaps, and which portions of the seed should be used as an input for which copy of the function f here is modeled by some combinatorial structure called design, some regression design. Basically, it tells you the partitioning or partitioning of the seed into overlapping inputs of the right size, and you apply f function to each one of those, and output is the output of the generator. So ignoring this fact that the inputs are kind of overlapping here, the truth table output by the generator, if you want to compute it at position I, you just need to apply the function f to appropriate input, and out comes the bit in position I. And because the function f itself has small circuit complexity, you can compute each bit of the generator output by small circuit complexity intuitively. Make sense?
Where's the
Poly n comes from the design computation. So there's a little bit of work. So if you tell me the index I need to figure out which subset of the bit location of the seed to use to apply your circuit for F2. and that's a polynomial overhead. Fortunately, the designs themselves can be efficiently constructed. So it's an explicit construction of how to partition things. And this is polynomial overhead that we can tolerate.
So this might be a trivial question. I thought the explicit one was only with small stretch, right? But if you have large stretch.
But it's exactly the case we want, small stretch.
Okay. So in the large stretch case, we don't know of a local PG.
The super large slope stretch, we don't have a good design construction, but super like exponential stretch will give you like exponential time learning algorithm. So I don't know if you're really willing to pay for exponential time learning algorithm. It's close to trivial one. There may be some small constant improvement. So yeah, so like exponential stretch where these guys are hard to find may not be even worth doing. But honestly, I'm not sure what happens.
But we don't know any better than this greedy algorithm.
That's right. That's right. That's right. Yeah. But if you're an exponential time regime, maybe exponential time is okay for you to pay, right? Because you're going to be running an exponential time learning algorithm anyway. So maybe it's okay. You can absorb those costs possibly. I haven't thought about this, to be honest. Yes.
Could you repeat
Yeah.
the question?
So the question is, and maybe somebody also can answer, and I can repeat the answer. Why did Rasborov need locality in his paper on proof complexity for the PRG?
Oh, it was the proof.
Yeah, there was a proof complexity paper.
Oh, I see it, yes.
Because you want to show it's hard to prove MCSP natural properties from just a proof complexity generator, which if it's not local, there's no connection. I think it's the same thing as
Right.
why you need it here.
I think he answered his own question once I repeated
I
it.
think it's 2002, but okay, maybe it was.
Yeah, it's a long time. It's good to repeat questions sometimes. Right. So how do we use this MCSP to learn? We play to lose. And this is a nice way to play. So you set up the game in such a way that you will definitely lose at the game. So I suggest you all do that. And so in this case, what it means is you set the parameters of your generator, like a stretch parameter, in such a way that MCSP will have easy time breaking it. And why are you rooting for MCSP? Because if MCSP breaks a generator, you get a learning algorithm. So if you want to get learning, you want the generator to fail, to be broken by MCSP, and you set the parameters so that it does happen. And as I said, you like want a polynomial time algorithm, so you want to get a polynomial stretch. And your MCSP will work very hard. So you set the threshold parameter to be like exponential in L, where L is the input size of your function. And by choosing the parameters appropriately, the outputs of the generator based on function f, say of polynomial size, will be of exponential but smaller than 2 to the L over 2 circuit complexity. Whereas for your random string, its complexity will be close to 2 to the L. So we'll have a gap between 2 to the L over 2 and 2 to the L. And therefore, your MCSP will be able to break the generator. And it will do it in polynomial time for you because the stretch we set was polynomial in the input size of the function f. Okay, so in the end, you get the Nissan-Wigderson algorithm that will compute the function f. So it will produce a circuit which computes the function f significantly more than 50% of the time. This 1 over poly was 1 over capital L before, for people who are like following this. So still, and our stretch is polynomial, so it's non-trivial advantage over 1/2.
This is with an MCSP work.
This is, yeah, you see it right here?
Yeah.
Yeah, definitely. We'll work on that. But yes, thank you for observing this. Yeah, definitely. So MCSP is used by the learning algorithm to get a learning algorithm with membership queries over the uniform distribution. And we haven't gotten even the function f approximated well enough. It's only like better than 50%. But that's easy to fix. I already mentioned that, but to get this result, you just set the polynomial stretch and set the parameters appropriately, and things just work out. So let me talk about some improvements you can do. First, you can make a better learner. So instead of like better than 50% of the time, you can get your function 99% of the time by doing the boosting trick, also known by the name of Yau's XOR lemma. So instead of learning function f that you actually want to learn, you'll define the new function f prime, which is like XOR of k copies of the function f on k independent inputs. So f prime is given k independent inputs, x1 through xk. You apply f to each one of them and then XOR the result. So f prime is also a Boolean function, since f was a Boolean function. And moreover, f prime is not much more difficult than f was, because you're basically using f and you use the circuit for f like k times. If k is small, and it will be small, it will be the most polynomial in n, then the circuit for f prime will also have polynomial size, because the function f was of polynomial circuit complexity. So now we like switch the game for the poor learning algorithm. So now the learning algorithm must learn f prime instead of f, and will do so only with like better than 50% chance. But it's good enough. If we get f prime better than 50% chance advantage, then there's a way to recover from it a small circuit for original function f that we care about, and that will compute the function f with 99% chance of success. Actually, 1 minus 1 over poly. So this is kind of a boosting where you have a weak learner and you use it to get a strong learner by taking the function you want to learn and kind of encode it in some error-correcting way, and then run the weak learner on the encoded function and do the decoding of the encoding to recover the circuit for original function. Okay, average case MCSP. So now things become a little bit more interesting, or quite a bit more interesting, I would say, because the oracle for MCSP was a bit too much. To break the generator that we set up, it's really enough to distinguish the outputs of the generator from random. So I don't really need to be able to tell on every simple string, simple truth table if it's simple, but just on average. Okay. So I don't really need a strong algorithm like an MCSP algorithm, but I can get away with something which is like an average case heuristic for MCSP. Another way, so an efficient heuristic for MCSP would be an algorithm P, which has the following property. For every easy truth table, like easy, think about small size, like polynomial size, for example, the heuristic algorithm says yes, easy, 100% correct. And on a random one, it may say sometimes easy, sometimes hard, but for at least 50% of the random strings, the algorithm will say, no, it doesn't seem to be easy. So sometimes it says no on easy things, but easy things are very few. The fact that the algorithm says yes on all the easy ones is a huge advantage, because they're so sparse in this whole space of random things that being able to say yes on all the easy ones and have some tiny error on the rest is huge, very useful. Yes. And this definition is exactly or pretty much the same as the definition of a natural property given by Rasberov and Rudich in the context of circuit complexity that Rahul talked about. In their language, it would be like a natural property useful against size S, where S is this size parameter for the easy functions. Equivalently, you can talk about this as like zero error average case heuristic for MCSP, or I think about it as like one-sided average case heuristic, which turns out to be exactly the same thing for this problem, even though generally like one-sided and zero error is not the same, but like for this problem, it just happens. And why I call it one-sided is because you always have to be correct on the easy ones. So on this side, you're always correct. And here for random ones, I give you some slack. But because there are so many hard ones that being incorrect on there sometimes, yeah, it's okay. It's okay. It's minor offense for now. The good thing about this is that such heuristic algorithms are enough for the learning application that I told you about. So Nissan Wigderson just needs to be broken. You don't have to have MCSP algorithm to break it. You just have to have something which will always output yes on the pseudorandom part, which happens to be easy, and heuristic here gives you that. And on the random things, it will not say easy too often. So that's enough. Okay, so now to Robert's question. So finally, we can have a setup where we can get rid of this MCSP oracle and get an unconditional learning algorithm for some circuit class using this framework I described. And what we're going to learn is the class of AC0 circuits with mod P gates for prime P. So AC0 mod P gates are circuits of constant depth with ANDs, ORs, and NOT gates, as well as some mod P gates, which for the purpose of this talk will be denoted by plus, like parities. But parity can be mod P gate for any prime P. So these circuits are it's a model that we understand reasonably well. And there are strong lower bounds known for explicit functions like majority against this class of circuits. So like majority requires circuit of this type of exponential size, so exponential like to the n to the epsilon kind of exponential. Let's call it weakly exponential size. And these are famous results from the golden era of circuit complexity due to Rasborov and Smolensky. Moreover, such lower bounds contain in them something nice, namely MCSP heuristics. So the proofs of these lower bounds are natural in the sense that you can extract from them an average case algorithm for AC0 mod P MCSP version. Thinking about this, it's like pretty amazing that Rasborov and Rudic in their natural proofs paper showed this result, and they had to work pretty hard to take this Rasborov-Smolensky lower bound and make it into an algorithm. And their purpose was just to make a point that their notion of natural proofs is applicable to all the lower bounds up to date. And so they were not lazy to take time and figure out how to do it for AC0 mod P circuits. But for them, it's just like another case in their longish paper saying, oh, this is natural proof, this is natural proof, this is natural proof. And yeah, this doesn't look very natural to begin with, but with some work, we can make it natural as well. And they did. And finally, sorry?
What did they have to do? Why wasn't it natural?
They had to do some linear algebra to make it natural.
Make it large enough?
Make it large enough, yes. Yes, basically make it large enough. So the largeness was not there to begin with. So they had to argue that the largeness can be made sufficient. And that involved some looking inside and opening the black box of the proof and figuring out what it's relying on. And they came up with an average case heuristic for MCSP for AC0 mod P circuits for size up to weakly exponential. So again, it's not full-fledged MCSP, it's not worst case, it's only average. It's for a special class, AC0 mod P. And even then, the size parameter cannot be very large, but it's weakly exponential. So that's great. That's what I just said. So now to learn a function f, which has polynomial, say, size circuits of this type, AC0 mod P, we need to play this game, play to lose game. And as I mentioned before, the runtime of your learning algorithm that you get. So now think about, you have some kind of MCSP oracle, average case, which is good enough. So now we're playing the game that I described earlier, just going to set the stretch and play to lose so that the MCSP algorithm of Rasborov and Rudic will break the generator. Ideally, we would like to set the stretch to be polynomial, and then we will get a polynomial time learning algorithm. That would be too good to be true. So it turns out that you set the stretch to be quasi-polynomial rather than polynomial. And the reason it has to be quasi-polynomial rather than polynomial is that their average case algorithm doesn't work for exponential circuit complexity, but only weakly exponential circuit complexity, okay? So they left something for us to do. So weakly exponential circuit lower bounds is the best we know so far, and there's a good reason for why. But weakly exponential gives you quasi-polynomial stretch is sufficient, and so you'll get quasi-polynomial time learning algorithm out of this. So it works out that capital L is quasi-polynomial, little l, the input size of your function that you're going to be, the output of the truth table output by the generator will be of size to the little l, so l will be the complexity parameter, and the threshold is set to be exponential, weakly exponential in little l, and the output of the generator is 2 to the little l, which is 2 to the polylog, which is quasi-polynomial. And as a result, you get unconditional, randomized, quasi-polynomial time learning algorithm for this class of circuits, AC0 mod P, under the uniform distribution only, and with membership queries, unfortunately. MCSP has been taken care of. So previously, a famous result by Lineal, Mansour, and Nissan gave a randomized quasi-polynomial time learning algorithm for AC0, so without mod P gates. And their approach was quite different. Their learning algorithm was also using our understanding of AC0 functions, easy IC0 functions, and the property those guys have. But those properties are taken care of by some kind of Fourier reasoning. And so they use Fourier analysis of Boolean functions to get the learning algorithm. We use pseudorandom generators and the connection between circuit complexity and pseudorandom generators to get this result for AC0 mod P circuits. Like Fourier doesn't seem to be enough for our purposes for learning there.
What if you use the same approach, but for AC0, like your approach for AC0?
Very good question. So if I understand your question correctly, are you saying like, can we break the PRG for function f coming from AC0 and get the same result? Yes, you can, because AC0 is a subset of AC0 mod P. So for a trivial reason, you can learn AC0. However,
but the natural proof for AC0 is similar, right?
Very good, very good. However, unfortunately, the locality of the Nissan-Wiggins PRG has this pesky overhead term to compute the designs, which is class poly n. And there's an efficient way to computing the designs, which unfortunately use some mod gates. So we cannot really compute the designs AC0 style. Actually, there's a lower bound that AC0 circuits cannot compute designs with the properties that we want. So you cannot use the same framework, unfortunately, for AC0 with a simpler natural property for AC0 because of an extra overhead of the PRG that is needed there. Yeah, very good question. So thank you so much. Any other questions? Question, yeah, please.
This lower bound you mentioned for AC0 computing these, is this for just specifically these combinatorial designs, or just for any like construction that has this reconstruction property?
It's for, yeah, so it's basically for the definition of designs that you want. You want a function that splits a set into subsets with small overlap, okay, and has enough of them. So if you want the properties like that, then AC0 cannot compute those things. Yeah, so I just find it a nice, lucky coincidence that Rasberg and Rudich took their time to come up with a one-sided average case heuristic for AC0 mod P MCSP. And finally, it has found its niche and an application in the constructive way of getting learning algorithms. So somebody, I often teach a course on algorithms, and somebody said that like if you have a good algorithm, somebody will find a way to use it for good. So here you have a good algorithm for natural property for AC0 mod P, but finally it was used for good, not just to prove a point, but actually for an algorithm. To summarize what I said so far, Nissan regression generator, a particular version of complexity generator that was useful for these purposes, plus MCSP heuristic or average case heuristic, also known as natural property, two ingredients that can give you learning algorithms in a general setting. And if you can instantiate that, like for AC0 mod P, you get rid of MCSP because there's an actual algorithm there, and you get this kind of learning. One thing that would be nice to get is learning from random examples alone and not use membership queries. That would, for AC0 mod P, for example, okay, we have unconditional algorithm that learns AC0 mod P, but uses membership queries. Lineal, Mansour, and Nissan managed to learn AC0 with just random examples, no membership queries. Here we need to use random examples because we need to use this Nissan regression generator intuitively. And it would be very interesting to get rid of this membership queries. I think you would have to do something completely different. That's why it's an interesting question. You can't just like look at things on regression. Maybe you can, I don't know. Maybe I wish I can, I'm not sure. But it's a difficult question. It would require new insights. Okay, so I have a few more minutes to tell you about more abstract framework. So if you think back, what we did with Nissan regression generator is it's a special case of the following more general scheme. So you have some secret string, call it F. So here in green, it's what we did for Nissan regression, and on the left-hand side, I'm saying what will be like the general framework. So how you can think of Nissan regression as a special case of a more general thing. So you have some secret string F, function you want to learn, truth table of function you want to learn. Then you have some kind of generator. In our case, it was Nissan regression generator based on the function F. In general, it will be a generator which will use the secret string in some way. Okay, and we'll have some stretch, mapping relatively short string to relatively long strings. Okay, then your task will be to distinguish the generator's output from uniformly random. Why would you want to do that? Because the prize you get if you do so will be an algorithm to reconstruct your secret F, assuming your generator has some reconstruction property that I'm going to define in a moment, which was the case for Nissan regression. So what's the reconstruction property? It's what you think it is. If you have a distinguisher for your generator G sub F, then you get from it an algorithm to compute F, or maybe approximately, or maybe exactly, depends on the generator you use, given maybe some short advice. Okay, so what was it for the NW applications that we talked about earlier? You had a circuit which computes F approximately, and the advice you need is evaluations of your function F on a few inputs. If you have such a thing, you can get an algorithm to compute a string given some short advice. It's another way of saying that your string F has small time-bounded Kolmogorov complexity, because you can compute F efficiently, have an algorithm for that. And to do the computation, you only need to be given some short advice. So that's the Kolmogorov description that you're given to your reconstruction algorithm, and then your reconstruction algorithm works efficiently, and you compute the string F. Okay, so if this framework works, then you get some sense of an upper bound on the Kolmogorov time-bounded Kolmogorov complexity of your string F using this framework. And as I suggested, we all should play to lose. Right? So you choose your GF carefully so that the output of your generator is compressible. For the Nissan regression, it was captured by the definition of locality of the generator. And then you use some heuristic that can test for compressibility. I used this MCSP heuristic, or average case of this, one-sided version of MCSP, but you can use any of the Kolmogorov complexity measures that you know and are friends with here. Yes. And if you do so, then you get the meta-complexity heuristic here that is useful, like if it's like, yeah, I'm going to get to that point in a moment, but like this meta-complexity heuristic here will allow you to learn F or construct F, which will give you an upper bound on the Kolmogorov complexity of F. So like Kolmogorov complexity is used in two places, like assumption and the conclusion. Right? And this brings us to this bridge between worst case and average case complexity. So as I just mentioned, to break the generator G sub F, you only need to have some average case heuristic, maybe one-sided or zero error ones, whichever you like. So this is an average case assumption, but the algorithm you get to recover a secret string F is worst case. It works for every F. Okay. So your assumption is about average case easiness. So something is easy to do on average. Your conclusion is that worst case, every string F has small Kolmogorov complexity of time-bounded kind. So natural property for our example that we used before, it's an average case heuristic, average case algorithm. And by the way, we don't know like worst case heuristic for MCSP mod P. That would be amazing if we did, but average case is enough, and that was lucky. But average case heuristic here gives you worst case learning algorithm on the right side. And this bridge from average case heuristics for compressibility using this generator-based approach to worst case conclusions is something that Shuichi Hirahara really took to the next level, and he'll talk about in his talk at some point here in the bootcamp. I just want to finish by mentioning a couple of examples of generators that what can you use. So NW-PRGs is just one example. You can use other PRGs, and I'll talk about some of them in the next hour. You can also use extractors, which are other kinds of generators. Or you can use something very simple like direct product constructions, maybe some error correcting code direct product construction of, or just take a function and do the direct product construction of the function. And I'll mention some of those things in my next hour. But the point is you have a framework, and then it's up to your imagination what kind of generators to plug in and what kind of consequences to get. So you have lots of objects out there on the shelf to play with. So just figure out what works for what. And applications of this kind of approach is to learning that we talked about, worst case to average case reductions for NP that I mentioned, that Shuichi might talk about. This problem that Rahul mentioned, understanding the relationship between algorithmica and heuristica, or in other words, if you have like an average case algorithm for SAT, can you solve SAT worst case efficiently or somewhat efficiently? Okay, can you convert average case easiness of SAT into worst case easiness of SAT in some way? As well as some circuit lower bounds for MCSP and the relatives that I'm going to talk about after the break. Thank you. Thank you.
Yeah, so in the last slide or two slides before, breaking. The pseudo-random string.
So basically, break-in generator makes sense only if a break-in generator will give you something interesting. So your generator must have some special properties, like reconstruction properties. That's the main thing. Okay, you break something that has the reconstruction property. Where do those properties come from? Usually, like in setting on some Wittgenstein generator or complexity generators, you say that my generator is going to be pseudo-random. Good, because if you assume that my function f that the generator is based on is of high circuit complexity, for example. And the way you prove that my generator will be good if function f is hard is by getting this reconstruction algorithm. Okay, so in some way you have like this, your proofs of something being good are constructive. Okay, to prove that hard function f implies the generator is good is done in the opposite direction by saying, okay, break my generator, I challenge you. Then I get your circuit for breaking it and make a small circuit for f from it. And that's the construction property of the generator. Another example would be for like aircraft encodes, decoding aircraft encodes, right? You say, I can decode with some error using, if you give me a message which almost matches the encoded version of the message, then I can correct for some few errors. So if you, and the hybrid arguments, of course, are very useful in pseudo-randomness setup. So usually the first step you do when you say that you can break the generator by distinguishing from random is to apply the hybrid argument and say, oh, therefore I can predict one of the bits of the generator and then go from there. So the hybrid argument is definitely used there. And that's why I use this, the generator versus the uniform random distribution. And then you can do hybrid and then you can focus on a particular bit of the generator and then use your properties of the generator to argue something good from it. That's what some Peterson did, and in another context.
Yes. So you said that all you need for the learning algorithm is an average case or heuristic algorithm for MCSP or natural proof. And we don't know any worst case version of it. But can you think of any clever way to use the worst case version of it? Is there anything known about what would follow if we did inside the set of learning algorithm?
If I had a worst case, would I get a better learning algorithm than what I had? It's a good question. I don't know the answer to that.
Just want to answer related. I say, okay, we should have some kind of worst case algorithm for HZOP and CSP. For some approach for
should we have?
And just by saying the index is proper. Yeah, exactly. Oh, it's proper.
Oh, yeah, proper and proper. Very good. Yeah, I meant to say this. So here it's like improper learning because the circuit that I get for my AC0 mod P function will definitely not be AC0 mod P circuit. I forgot to mention this important detail. So this is interesting. Like for improper learning, we have an algorithm here. I'm not sure we have any algorithm. I'm pretty sure we don't have any algorithm that properly learns AC0 mod P, but I'm not sure if we have some like barriers to that, maybe some crypto based. Do you know? Yeah.
Just a related question is if the distinguisher is AC0P, like does the analysis give you then that the learner, that the thing you get out is AC0P?
Some error correction, which probably.
Yeah, there's also some error correction that's going on, like Yal's XOR lemma, remember?
Okay. It's much more because it's because the natural. Okay. Yeah.
I think Rahul and Inger looked into this, and I think the best they could come up with like TC0. So it's kind of a construction thing for the complexity, because yeah, TC0 is enough to be like error correcting code.
I've kind of a naive question. So like, so it seems like in some sense you could think of this as kind of like a search to decision reduction, right? Because it's like I have a decision algorithm for MCSP and I'm using it to.
Absolutely. Yes, absolutely. Yes. So you have a decision algorithm for MCSP and you use it to find a small circuit, which is like solving a search version of MCSP, with some caveats that it's approximation rather than the exact circuit.
Right.
And it's not going to be like optimal size, but like polynomial related to the optimal size. But other than that, yeah, it's going to be search precision.
But I see also that one is a bit super efficient, right? It can be like it's that much less than that. So.
That's right. Yeah. So it's efficient, but with some other caveats. So yeah, I mean, definitely some very interesting phenomenon happening here.
I see.
Okay, so you